Professor Seiberg.
Okay. Thank you. Can you hear me? It's really a pleasure to be here and give this talk, except that this thing doesn't work. Okay, so it's a pleasure to give this talk. Before I start, I'd like to ask two things. First, give me a show of hands. How many of you are first-year students, and how can I turn off the audio here? How many of you are first-year students and second, third, graduate students, retired faculty? Okay, so the other comment is about how we handle questions. I'll be perfectly happy if you have an urgent question to answer it in the middle. So if there's something very urgent, please raise your hand and I'll try and find the appropriate time to let you ask. But independent of that, at the end, I'll be happy to answer questions. Even after we leave here, I can stay longer if you're interested. So let me start with the title, What Happens at Shorter Distances? A part of the talk will be about answering this question, but more interestingly, the main point of the talk will be what the question actually means. And it turns out that what the question actually means is a very, very deep issue in physics that has been dominated science more generally over the last several centuries. And however, it will come to an end. So the main lesson I want to get out of this talk is what the question means and how it might also mean nothing. So with that introduction, let me start from an example where the question of what happens at shorter distances is really important, and it will demonstrate it, and then we'll go into more interesting things. So as we will see, when we discuss different length scales, different disciplines are appropriate. And there are different descriptions of phenomena around us at different length scales. So I'll start with something which is kind of trivial, and gradually we'll go into other examples. And the goal is to show you that this is a common thing in all of human knowledge. So let's start, we are interested in cars. At very short distances, we have an engine, and the person who builds the engine is an engineer or a mechanic, and they don't even need to know how to drive. They need to know how to design such an engine. Go to longer distances. There's a driver driving the car, and the driver doesn't need to know what's going on underneath the hood. All the driver needs to know is how to control the car and stay in the lane. So the knowledge the driver needs is completely different than the knowledge the engineer needs. As we go to longer distances, we have traffic control, and here we have urban planners. They don't even need to have a driver license to design the highway. So the lesson from that, which looks completely trivial, and why am I wasting my time giving a physics talk about driving cars, is that at different length scales, a different description is needed. And the description at a given length scale is to a large extent independent of what's going on at other length scales. Let me give another example, which is a little bit more sophisticated, associated with phenomena that all of us, whether physicists or not, were interested in over the past few years, and that's COVID-19. At short distances, we have a virus, and some virologists study the virus, and the characteristic length scale is 10 to the -7 of a meter. And here they study the structure of the virus, the RNA, maybe they design a vaccine. They do a lot of things like that. At longer distances, there's a public policy issue of how to keep the public safe. We want to keep 2 meters between people or 6 feet between people, and we should or should not enforce wearing masks. The people who decide about that do not need to know anything about the RNA of the virus. The RNA of the virus is completely irrelevant to the policy at 2 meters. And as we go to long distances, we would like to prevent the pandemic from spreading. So we cross the borders between countries. People are not allowed to come in or leave. People are not allowed to come in or leave. And that is a question of politics and international politics. And the people who do that do not need to know anything about the RNA of the virus, nor do we need to. They need to know the details of how droplets propagate between one individual and the other. So these examples are from kind of almost everyday life, but this kind of structure of a hierarchical structure of different disciplines addressing phenomena at different length scales is prevailing in physics, and it also in biology, chemistry, every turn of life. And it's actually been very important for the evolution of science as we studied nature. So we can say that nature has been kind to us. This separation of scales, this is actually a technical term, separation of scales, and allows us to study nature one scale at a time. We don't need to understand the intricacies of quantum theory to study physics at everyday life. When Newton found his equations here, he didn't know anything about quantum mechanics. Nor do we need to know anything about the structure of the universe to address this question. So the fact that we can address the nature one scale at a time is extremely pleasant. Otherwise, there would have been no chance that humans could understand it. If we were supposed to understand all of nature simultaneously, understand all the intricacies of quantum mechanics and the structure of the universe, just to understand how a body moves on an inclined plane, we would never get anywhere. So we don't need to understand everything simultaneously. Nature is kind to us. And Einstein said about that, subtle is the Lord, but malicious he is not. So it's subtle to understand it, and we'll give more examples how the structure could be quite intricate and quite interesting and quite subtle, but it's not as bad as it could have been because of the fact that nature is so kind to us. So let me say a few more words about this separation of scales. As I said, we have this hierarchical structure, and phenomena at one length scale are almost independent of what's going on at other length scales. So we don't need to understand everything simultaneously. Otherwise, it would have been impossible to understand it. In that sense, nature is kind to us. Let me give another example of that from physics, and an example that will come back later in the talk. And this is the study of hydrodynamics. This is the study of how fluids flow, hence the word hydro, from water. I think it's Greek. And here is the flow of water. That was understood in the 19th century. It is described by a partial differential equation. Some of you might even know what a partial differential equation is. And some of you maybe even encounter the specific equation of Navier and Stokes. But the important thing is not the equation or what it is, but there is a kind of detailed description of how water flows as a result of pressure. We put some pressure, and there's air on top, and there's water underneath, and there are waves in the ocean, and we can see the waves here. And we can understand what's going on here by studying this equation. Now, what really happens is not that. This is the 19th century physics description, but there's also a 20th century physics description. And the 20th century physics description is completely there. In fact, there is no clear separation between the water and the air, because if we look very close with a microscope, we will see that there are droplets of water coming out. And if we look even closer, we'll see that there isn't clear separation between the water and the air. Instead, what we have is a bunch of water molecules bouncing around with no clear separation between this is still water and this is air. There's more of this and less of the other, and gradually it changes. So we see here that, again, this separation of scales. And in order to understand the flow of the water, we don't even need to know that there are molecules. Not only don't we need to know that, the Navier and Stokes, who described these equations, didn't even know that there are atoms in the world. They viewed that as a continuous medium that changes in a smooth way. Now we understand better. We have these molecules. But for most applications, it doesn't matter. So if you design a water pipe, or you want to describe how the weather evolves and how the waves move, you don't need to think about the molecules. You can use the equations, the effective description of the flow of the water without ever mentioning the fact that, without even knowing that there are molecules underneath. So again, we see this separation of scales. So over the past several centuries, science has progressed in a two-way approach. First, we gradually went to shorter and shorter distances, uncovering deeper and deeper truth, deeper and deeper laws of nature at shorter distances. And the view is that the more correct, more precise description is the description at short distances, and the description at longer distances is approximate, but it's very effective. So we're gradually peeling the onion, finding more and more layers. It's getting more and more interesting. But the layers that we peel off, like these, they are not useless. They're still very good theories that we can study, and they're very useful. So we keep going on to shorter and shorter distances, uncover deeper and deeper truth. And so this is one direction, but this is kind of a two-way street. As we do that, we also move forward backwards and ask ourselves, okay, now we know the rules at some length scale. Can we use it to derive the phenomena at longer scales? Maybe we can even find new phenomena at longer scales. So what most physicists do is use known rules to derive what happens at longer distances. They know the rules that govern the behavior of atoms, and they try to design new materials or try to find new phases of matter. A small fraction of physicists move in the other direction, try to move down to shorter and shorter distances. And we'll discuss that in a lot of detail. So we refer to this description as an effective description or an effective theory. This is actually a very precise technical term, effective theory. At every length scale, we have an effective theory at that length scale. It is an approximate description. And that approximate description is effective because it's very useful. You don't need to know all the details of what happens underneath, what happens at shorter distances, and it can be used to describe many, many phenomena. So progress happens in the two directions, and progress even today happens in the two directions. As we speak, people both try to explore what happens at shorter distances, and at the same time try to use this knowledge of what's going on at shorter distances to derive phenomena at longer distances. So the long distance, or also called macroscopic, effective description gives us clues motivating us to search to what happens at shorter distances. So we have some description at some length scale. I'll give examples soon. And then if it doesn't work very well, what it means is that we don't have complete control over it, and we must go to shorter distances and correct the description and find a more complete theory down there. At the same time, we can also use this microscopic theory and derive new phenomena at long distances. This will give us both tests of our understanding, and at the same time, will also allow us to test both the test and to find new phenomena. And the beauty of science lies in both directions. We have simple underlying laws. The fundamental laws of physics are believed to be nice and beautiful. And at the same time, we get a very rich spectrum of complicated consequences from these simple rules. So these two things are beautiful. First, the fact that the underlying rules are very simple. And second, we get the whole richness of phenomena around us, going all the way to biology, and the fact that different people have different thoughts. All of these follow from the same simple rules at shorter distances. And as I said, these two lines of research are not independent, and there's an interesting interplay between them. And as we discuss this in this fundamental research, at the same time, we shouldn't forget that there are also technological applications. So as we proceed both inward and outward, there are technological applications that follow from this understanding. So being a little bit more concrete, let me describe one length scale is what happens in condensed matter physics or chemistry or material science. So these are all sciences that study properties of materials. And the length scales here that we start with is 10 to the minus 10 meters. This is the structure of the atom. We more or less understand what it is. That's the input of the short distance theory. And what we find at longer distances is a huge number of materials around us. And they're characterized by having different colors, different hardness, different viscosity. They might or might not conduct electricity. And there are all sorts of other phenomena that some of you have heard of. They could be superconductors, they could be semiconductors. There are all sorts of interesting phenomena. All of them start at short distances from the same atom and the same rules of the atom that we know and love. Another discipline that is interesting is high energy physics, also known as particle physics. So this discipline studies the matter fields, the matter particles, and the forces between them, study electrons and many other particles. So this is the story that comes here, comes under the name of the standard model of particle physics. We have a beautiful theory that describes all known phenomena at distances larger than 10 to the minus 18 meters. So this is 8 orders of magnitude shorter than the size of the atom. These are really tiny distances. And here we have particles like an electron and a positron, and gamma is a photon, is the particle carrying the electric field, the electromagnetic force, and these are quarks and gluons. There's a whole set of particles here. And we have a rather detailed description of nature at 10 to the minus 18 meters. It works extremely well. And we can derive from it all the rules about atomic physics and molecular physics and all that. They follow from these fundamental rules. And using chemistry, we can go to larger distances and describe properties of materials. So we have a very good understanding between 10 to the minus 18 meters and 10 to the minus 10 meters. And as I said, at larger distances, we follow the other disciplines. So at these distances, we have atoms. The properties of atoms follow from the structure of the standard model of particle physics. And it really begs the question, what appears at shorter distances? What are the rules? What is the physics at shorter distances that gives rise to the standard model of particle physics as an effective description at 10 to the minus 18 meters? We would like to go down to 10 to the minus 20, maybe 10 to the minus 30, etc. So at the moment, this is not known. This is a big open question in science. Hopefully, we will know better soon. But at the moment, we do not know what's going on at shorter distances. We have some clues about that, but we don't have a complete understanding. And as we go to shorter and shorter distances, we need a magnifying glass that would give us better resolution at shorter distances so that we can tell what's going on there. And the magnifying glass that we use is an accelerator. The state of the art is the LHC, Large Hadron Collider, at a laboratory called CERN outside Geneva. And there's some discussion of upgrading it and maybe build a larger machine that would have higher energy and explore nature at even shorter distances. Alternatively, as I said, we can stay within the same distances that we know and perform the measurements more accurately. So we can perform the measurements more accurately, do the calculations more accurately. And if we find a discrepancy, it means that our understanding is incomplete and we need to fix the theory. We need to understand different rules at shorter distances. So that's done in devices like that. That's in Fermilab. And I'll give now one example of how we compare theory and experiment, which will give you a flavor of how well we understand things. So consider an electron. An electron rotates around its axis, and as such, it becomes like a little magnet. So every electron behaves like a little magnet, and we can ask how strong the magnet is. So it has a north pole and a south pole, has a north and a south pole, and we can try and check how strong the magnet is. And we can calculate it using our theory, the standard model of particle physics, and we can perform the experiment. This is an enormous task. The result is the following. The theoretical calculation gives this number. The first digit here, 2, was actually found here in Cambridge. Almost every digit here, at least at the beginning, got a Nobel Prize. Was that significant? It was an enormously complicated calculation. So the 2 that appears here follow just from quantum mechanics and special relativity. The 002, this part, comes from a. And as we add more and more digits, various details of the weak force and the strong force come in. This calculation is incredibly complicated. As we add more and more digits, the complexity grows more and more. And this is the state of the art using the fancier methods that we have and very powerful computers. At the same time, experimentalists did the measurement. And this is the experimental result. And I don't know about you, but I think this is unbelievable. There is no other measurement in any branch of science, not a single one, that has that agreement between theory and experiment. It's not that it almost works. It not works up to a factor of 2. It works with so many significant digits. I think it tells us that we really know what we're doing. It's not an accident that theory and experiment match that well. When you do experiment here in the lab with theories that are well understood, if you get it up to 10% accuracy, you feel that's good enough. Think of the accuracy that you have here. This is really incredible, but I'm a theorist. So I think the theorists should view it as a challenge because the experimentalists are ahead. We should compute more digits and challenge them to perform the experiment better. And I really hope that at some point there would be a discrepancy. Because if there is a discrepancy and the measurement is correct and the calculation is correct, it means that there's something very important that we miss. And something very important would be a clue to what happens at shorter distances. So that's about the electron. We have a spectacular success. But the electron has a cousin called a muon. It's another particle very similar to the electron. It's about a factor of 200 heavier. And as far as the standard model is concerned, it's equally elementary. Just as we have an electron, the muon is also a fundamental particle, just another fundamental particle. And this is a picture of the device that measures how strong the magnet associated with the muon is. And again, we can do the theoretical calculation and we can look at the experimental result, and that's it. It starts with the same 2 as with the electron. The electromagnetic contribution, the 002, is the same. The 3 is already the same, but you see they start being a little bit different as we keep going. The calculation for the muon is harder and the measurement is harder, and that's why we have fewer digits than for the electron. But notice that they're not the same. They're not exactly the same. Now, what's going on here? Option 1, the theory calculation is wrong. Option 2, the experimental measurement is wrong. I personally think that the mistake is in the theory, but the jury is still out on that. But it's also possible that both are correct. And if both are correct, it means that this small discrepancy points to new physics. And the new physics that we don't yet know about that will explain why these digits are why these numbers are a little bit different. So let's summarize what we've seen so far. We talked about condensed matter physics and high energy physics. And the primary goal in condensed matter physics is kind of going outward. We have known rules of physics. These are the rules of quantum mechanics, Schrödinger equation, if you heard about it, and electrons and protons, and they all interact, attract, and repel each other. And all the beauty of materials around us comes from that. And that's a description that describes distances larger than 10 to the minus 10. We also talked about high energy physics or particle physics, describing what happens at distances less than 10 to the minus nature up to distances around 10 to the minus 18. And the goal in condensed matter physics is to go outward to larger and larger distances, and the goal in high energy physics is to go to shorter and shorter distances and see what clues we can get about what's going on there. Very surprisingly, the two disciplines are completely different, operating at different length scales. Surprisingly, they are being described using the same mathematical setup. So the fact that we use calculus everywhere, that we kind of got used to it. But the mathematical setup that we use both for condensed matter physics and for high energy physics is known as quantum field theory. This is a very sophisticated subject. I do not know at what year you study it here. Is it second, third year? Nobody knows. Okay, so some people here heard the name, and some people maybe even heard about it. And this is the mathematical language of both the standard model of particle physics and of condensed matter physics. And The nice thing or surprising thing that happens here is one of the deepest things in physics in the 20th century, is that in this case, the separation of scales and finding effective theories at different length scales is not just some qualitative set of ideas that appear a little bit vague, and a speaker coming here say this length scale, that's length scale, and an engine and a car and urban planning and all that. It translates into a very precise mathematical equation. And the fact that we have this separation of scales translates into an equation. It comes under the name of renormalization group, and many people contributed to it. I think the main contributors are Ken Wilson, who died about 10 years ago, and Steve Weinberg, who unfortunately died recently. And in this case, there's a certain equation that describes this separation of scales, and people can measure the consequences of that equation. So it's a very quantitative, very explicit result. So notice that Steve Weinberg died in 2021. In that context, I found a beautiful quote that he wrote in 2021. And he wrote, there's a school of philosophy of science associated in particular with the name of Thomas Kuhn that sees the development of science, particularly of physics, as a series of paradigm shifts in which our point of view changes so radically that we can barely understand the theories of earlier times. And what this means is that we have Newton's theory that describes the motion of body of everyday life. And at shorter distances, we have a new theory, quantum mechanics. We throw away the old theory, we forget about the old theory, we have the new one, which is more complete and better. Similarly, for motion at small velocities, we use Newtonian mechanics, but if we go to higher velocities, we know the Newtonian mechanics is not right. We should throw it out. We have instead special relativity, which is a much more complete theory. So this is what Thomas Kuhn thinks, but Steve Weinberg thinks this is wrong. I don't believe it for a minute. I think our successful theories always survive as Newtonian mechanics has, and as I'm sure the standard model will survive as approximations. This is what I said earlier. So first of all, Steve Weinberg is one of the founding fathers of the standard model of particle physics. He got the Nobel Prize for the theory of the weak force, but he also did many other things. But what he emphasizes here is that when we have these different theories, we don't throw away the old one. The old one is still a very good approximation. He is actually the person who coined the phrase effective theory. This was Steve Weinberg who coined that phrase. And the idea is that Newtonian mechanics is not accurate at short distances, but it is still a good theory. We shouldn't throw it out. And it's the fact that we have a paradigm change and we don't have to forget everything about the old theory is just completely wrong. And I completely agree with Steve Weinberg about that. So as we go to shorter and shorter distances, so we talked about condensed matter or particle physics, let's go to even shorter distances and address the most conceptual question in physics. And the most conceptual question in physics is to combine quantum mechanics and general relativity or gravity. The first person to address this question was Max Planck, and he addressed that toward the end of the 19th century. And what he did, he understood the Planck's constant h, or if h bar, if we put some factors of 2 pi, and he took all the constants of nature. So that is what today we call quantum mechanics. He didn't know it at the time. G is Newton's constant, and c is the speed of light, which was known at the time. And he said we can find something with dimension of length, which is today called the Planck length, in his honor, which is 10 to the minus 35 meters. And we can divide by the speed of light and find the Planck time, 10 to the minus 43. And what Max Planck said, and this is more than 120 years ago, so this year he had this insight long then, that as we go to these short distances, we have to consider both general relativity, both gravity, and at the same time, quantum mechanics. The two theories are both important. At long distances in physics, when we talk about motion of galaxies and all that, we can ignore quantum mechanics. When we discuss particle physics, we can ignore gravity. But when we go to these short distances, both for distances in space and short times, we cannot ignore them, and they are both equally important. So once we understand what's going on there, we should be able to understand the structure of the universe when it was 10 to the minus 43 second old. So this is really understanding the origin of the universe or the secrets of the creation of the universe. So Planck understood that already 120 years ago. And we are kind of behind with our homework because we still do not know the answer to this question. What happens at these short distances? So let me summarize all the scales that we discussed so far, and then go into a little bit more detail. We discussed the standard model of particle physics. That's 10 to the minus 18 meters. 8 orders of magnitude larger, we discussed atoms and molecules, like the molecules of water. And at even longer distances, we see all the matter around us. There we have the bread and the cheese and maybe some wine and a piece of wood and maybe some metal. And we also discussed the motion of water and hydrodynamics and the equations that govern the motion of the waves here. We still don't know what's going on at shorter distances. There are experiments going on there to see what's going on there. This is still a very hot field. And at even shorter distances, 10 to the minus 35 meters, really, really far away, much shorter, we need to put together quantum mechanics and relativity. And this is an intense field of study. And we don't yet have the final word about that, but the best candidate is string theory. So let me say a few words about string theory. How many of you heard of string theory? How many of you haven't heard of string theory? Wow. So what is it? It's an ambitious attempt to find a comprehensive theory of nature. It's really ambitious. And it should describe all the elementary particles like the electrons and the quarks that I mentioned earlier, and all the forces that operate between them, the electromagnetic force, the strong force, and so forth. But also describe gravity, the force of gravity. And we know from Einstein that the force of gravity is associated with the structure of space and time. So this theory should describe everything, both the particles and the forces, and to describe space and time itself. I'll say a lot more about the structure of space and time soon. And the reason it is hard is that we face enormous challenges. First of all, it's clear that we need a new conceptual framework. We need perhaps new mathematics to describe it. We don't yet have it. We do not yet have the fundamental principles that tell somebody, these are the fundamental principles, go and start computing. We don't know what they are. The second problem is that the length scales. We talk about the length scales of the quantum gravity, the Planck scale. It's way, way shorter than anything we can explore with our current devices. So when we do experiments at the LHC or at future colliders, we explore 10 to the minus 18 meters. But here we need to go many, many orders of magnitude shorter to explore the phenomena there. So we don't have experimental clues. Nor do we know the conceptual framework. However, we have a lot of clues that we are on the right track. Be extremely promising. First, if we just look at it even superficially, we immediately see that it has all the right ingredients to describe nature. It automatically includes quantum mechanics as a consequence. It automatically has gravity as a consequence. This is not something that we put in. It comes out of the equations. And it has the kind of forces and particles that we see around us in the standard model. The details do not quite work, but qualitatively, it looks very promising. None of these ingredients were put in. All of these ingredients come out without putting them in. The second fact, which I think is also quite interesting, is that it has surprising consistency. Every other attempt to put gravity and quantum mechanics together immediately leads to inconsistencies. We start computing something and everything is infinite. We don't know what the equations mean. The equations don't have solutions. It's terrible. Here, miraculously, all the bad terms drop out and everything works. And this is enormously satisfying. But it also tells us that we really don't know what we're doing, because if we are surprised by cancellations, it means that we don't know why it happened. One should not be surprised. If you really understand something, you're not surprised by the cancellations. It had to work like that. So that's not the case here. The other aspect is that signals that this is a deep intellectual structure. is that it is independent of describing the quantum gravity. It has already had a huge impact on other branches of physics, including mathematics. So ideas that came from string theory found their way into condensed matter physics, found their way into nuclear physics, and even magnetohydrodynamics. There are all sorts of branches of physics. Even more surprisingly, they found their way to mathematics, completely revolutionizing some branches of mathematics. That's the sign of a deep theory. See, Newton's theory of when Newton invented calculus, it was invented for one purpose. But as time passed, calculus found its way to many other branches of physics. Almost every branch of physics uses calculus. Even chemistry, and even sociologists use calculus. So that's a sign of a deep structure. The structure that was invented for one thing and has lots of different unexpected applications. So string theory is like that. It's a machine that produces answers. That's a sign that we are on the right track. It cannot be a coincidence that playing with string theory, all sorts of new ideas in mathematics and in other branches of physics come out. Accidents don't happen accidents like that don't happen. So I said that string theory should also explain the structure of space and time. So what is space? So all of us have some intuition about space. We can move up and down and right and left and forwards and backwards. Some of us ever heard about higher dimensions, or we can also move in higher dimensions. So we all have some intuitive notion of space. In relativity, space can change, especially in general relativity, space can change. And that makes it more interesting. In string theory, there's I believe that the notion of space can be an emergent concept. So let me say a few words what that means. So earlier we talked about the surface of the ocean with its waves. So here we have water, and here we have air and some molecules. So if we look from afar, it looks like there's a smooth surface, which perhaps with some wiggles on it, the waves. But if we look closer, we see that the surface is not sharp. There are droplets that move in and out. And if we look even closer than that, we see all these molecules. There's no clear, well-defined surface. So the surface of the water, we say, is an emergent concept. It's a derived concept. Looking at short distances, there's no surface of the water. It's an illusion that there is a surface. At long distances, we have such a structure, we have such a surface, and it looks relatively smooth. So the surface of the water looks like a two-dimensional curved surface, but looking closer, there's no clear surface. It's only an approximate illusion. We have an effective description in the sense that, as I said, Steve Weinberg coined. We have a macroscopic theory controls the surface of the surface. It's called hydrodynamics, and it's described by this equation of Navier and Stokes that I mentioned earlier. So I'm going to use that as an analogy how space can emerge. So the idea in string theory is that we use something very similar. The surface of the water will be our emergent space. Just as here we have an emergent two-dimensional space that changes in time. That would be space itself that we live in. Our three-dimensional space would be as emergent as the surface of the water. Hydrodynamics is the effective theory that describes differential equation that describe the shape of the flow of the water or the shape of the surface. And that's the analog of general relativity. General relativity is also a partial differential equation that describes how space itself curves. And that's the analog of the equation that describes the surface of the water. But the more complete description that operates at short distances, in these analogies, we have the water and air molecules here, and the analog of that is string theory. So at very short distances, this is the correct description. This is the complete description. And then we have an emergent space, which is described by some differential equation, very much like in the surface of the water. So let's assume this is indeed the case. There's a lot of evidence that this is the case, and in simple cases, get more and more complicated cases, we see this happening in reality. So if space is indeed emergent, the fundamental description breaks down at shorter distances. So just as the surface of the water is a kind of an illusion, it's not really there. And if we look close enough, we can say, is this in the water or in the air? If we look very close, we can't tell. Similarly, if we start looking at space itself at very short distances, we will not be able to see any space. The fact that there is space is some illusion that we have, some approximation to something more fundamental. So if space emerges as an approximate notion, so will the notion of distance. So once we go to very short distances of the order of 10 to the minus 35 meters, we cannot tell what distance means, because the whole idea of distance will be an approximate notion at long distances. So if we try to look at very short distances, we cannot tell what the distances mean. So we cannot discuss space at distances shorter than 10 to the minus 35 meters. There's a lot of evidence that this statement is correct. If you ask most physicists who thought about that, will tell you this is definitely true. That's actually extremely interesting. So if space is indeed emergent, it means that at short distances, we can no longer discuss the notion of distance. The notion of distance is totally meaningless. This is some kind of an approximation that we have at longer distances. So space itself becomes some kind of a fuzzy notion, a notion that we cannot describe in detail because it doesn't exist. It exists only at longer distances. Now, here I talked about space. What about time? So we all have some intuitive notion of time. The talk is been already 40 minutes. Some of you would like it to end by now, but hang on, it will end soon. But we all know what time is. There's past and there's present and there's future. So we all have this intuitive notion. And physics is about time evolution. What you do in physics, you describe some initial conditions and you let the system grow, and you should predict how the system evolves. You make a prediction about the outcome of an experiment, and later, I underscore later, you do the experiment and check it. You don't make the prediction after you do the experiment. There's some notion of causality and cause and effect, and the cause happens before the effect. You cannot go back and kill your grandfather. You know, this is a known statement about physics and real life. Now, Einstein's theory of relativity mixes space and time, already mentioned that. And therefore, if we accept the space is emergent, it doesn't take a lot of imagination to say that time will also be emergent. Now, if time is really emergent, it's very confusing. First of all, we have no idea as of today what it means. There isn't a single example where we know what time is emergent. That's a big challenge. Maybe one of you, the young physicist, will do it in the coming years. But understanding how time emerges will explain what it means that the universe is created. Because we could ask what happens at very short distances. We said 10 to the minus 34 seconds. What happens before that? The notion of time will cease to make sense. And therefore, we cannot ask what happened before the Big Bang. What happened at very short times, because the notion of time does not make sense. So we'll really understand what creation means. Creation means that space and time, something that looks approximately like space and time. So let me make some more comments about space and time. If there are indeed emergent quantities, there's an ultimate distance and shortest time, 10 to the minus 35 meters or 10 to the minus 43 seconds. Nothing happens at shorter distances. It's not that nothing happens there. It's not even meaningful to ask what happens there. So there's nothing meaningful at shorter distances. The notion of distance and time are some kind of approximate illusions. And we cannot ask what happens at shorter distances. This was the title of this talk. So one lesson from this talk is that we have a sequence of theories going to shorter and shorter distances, finding deeper and deeper truth. And then the question itself ceases to make sense. We cannot find a deeper theory at a shorter distance because there's no such thing as shorter distance. There's an ultimate discussion. There's an ultimate distance, a very short distance. So our understanding of the law of nature, this peeling of the onion that I talked about earlier, going deeper and deeper, will come to an end. In philosophy, this is known as reductionism, the fact that every phenomenon is explained using deeper truth at shorter distances. This is known as reductionism in philosophy. This is centuries ago. This will come to an end. And this can come to an end within a decade, maybe at the time you guys are professional physicists, and maybe it will take longer, we don't know. I hope it will be soon, at least so that I can understand it, if not, find it. And that would be the end of this reductionism. Reductionist pursuit to deeper truth at shorter distances, because there is no such thing as shorter distances. So let me summarize the talk. The first lesson is separation of scales. We said that nature is kind to us. Our understanding at different length scales can be done independently of what's going on at other length scales. Recall the examples with the car, the examples with COVID-19, and then I talked about condensed matter physics, material science, quantum mechanics, going deeper to particle physics, and even string theory. So going to shorter distances, we find deeper truth, and this is this reductionism of the philosophers. We discussed physics at different scales. I did not discuss in detail here geophysics, astrophysics, cosmology. This is going to longer scale, just a second. And we also talked a little bit about materials around us. And then we go down to shorter distances, quantum theory, atoms, molecules, etc. We talked about the standard model of particle physics and its ingredients, electrons, quarks, Higgs bosons. I didn't say much about that, etc. Then we don't know what happens at shorter distances. This is still an open question that people are interested in. Experiments are going on to uncover that, and there's some theoretical idea. And at very short distances, we discuss quantum gravity, and in particular, string theory. And in this context of space and time appear to be emergent. That by itself is a huge thing. Just imagine that everything, all the space that we know about, and even more so all the time that we know about, are all derived concepts, and they are not there in the fundamental formulation of the theory. But if that turns out to be the case, this would be the end of reductionism, because we cannot ask what happens at shorter distances. There are no shorter distances, and therefore we cannot ask about it. So once this is understood, this thing of going to shorter and shorter distances will come to an end. We kind of peeled the onion and there was nothing left to be found. And some people like to call it the theory of everything. I don't, for reasons I will soon explain. But I think calling it the ultimate theory will be a justified term, because there will not be any theory at shorter distances. There will not be deeper truth at shorter distances. The reason I don't like to call it the theory of everything is that this will not be the end of science. So if you think this will happen, say, in your lifetime, and I think it's actually quite likely that it will happen in your lifetime, all this will be understood. This will not be the end of science, because recall that I said that we pursue what happens at shorter and shorter distances, and at the same time, we also go the other way and try to find new consequences of known rules. And that will probably take on a long time. So this will not be the end of science, but it will be a very interesting point to understand the ultimate theory. So I'll stop here. I'll thank you, and if there are questions, I'll be happy to answer.
Thank you so much, Professor Seiberg, for the fantastic talk. We do have time for questions now, and we're going to be using our famous box. So, do we have any questions? Anyone?
Can someone explain what space and time then emerge from?
That's the big question. It does not, it will emerge from some other description where there will be no space. So we don't know in general. So first of all, for time, we don't have the slightest idea. Let's get that out of the way. For space, we do not know how space that we live in emerges, but we have examples where similar kind of spaces do emerge, spaces that do not exist. And in the fundamental formulation, it's not even that there is something that's similar to space, it just pops out of nothing. And there are various examples which are studied at various levels of detail in different number of dimensions with different curvatures and different technical terms, where we know how to do that. None of them is as good as we would like for the real world, kind of derive flat space as we see it. But this is a very hot topic, and many people are working on it. So I didn't give you a good answer because there isn't a good answer. And I think that's why we need young people like you. So you study a few more years here, and then you go to graduate school, and then you do research, and then you figure it out. So on average, say 8 dozen years, one of you will figure it out. And this will be something that will be remembered for centuries, not just say for a year or two. Answering your question will be something that, you know, in 500 years, people will still discuss, because it will be the ultimate theory. It will not be superseded by anything more fundamental. So you're at a fantastic time where this can be done. And I really encourage many of you to do it. Wow, good catch. So various people have all sorts of suggestions. As far as I can tell, they do not even come close to the achievements and the reasons to be excited about string theory. This is not a sociological question. It's not that there's some group of old people behind closed door, maybe in a smoky room, who decide which theory is right and which theory is not. That's not the case. And many of us, I did not look in detail in all of these attempts. Many of us would be delighted if there's a better theory. I'm not personally attached, I'm attached a little bit, but I'm not 100% committed to anything. If there's anything better, I'll have no problem working on the better theory. But it's not even close. And we can get into various technicalities of why it's not even close. But independently of the technicalities of why it's not even close, is that the impact that string theory has already had on other branches of science, including other branches of physics and mathematics, is undeniable. So even if you forget everything else, just that has already been a good investment. And for me, this is a sign, just like calculus, that we're on the right track. If we have something that keeps producing new results that were not intended, it's not random. There's a very interesting, deep intellectual structure that we are trying to explore. Now, in the past, there were some various other suggestions that appeared to be different. And then you could have asked your question about them. Some of them turned out to be part of string theory, and it took some time to realize that it's actually part of the same theory. Others either do not make sense, or I don't even see how they could possibly be connected. So I think there is one big intellectual structure that we are still really at the beginning of understanding. And personally, I think it's on the right track. But in science, there's no guarantee. It's not like, you know, you buy a washer with the 10-year warranty, and you know that it will definitely break in 10 years, because that's what the warranty is all about. It's not like that. You don't know when the discovery will happen. And that's what makes it exciting, because we're constantly surprised. So we don't know when we'll find a better answer. No applause here. Because I mentioned this two-way street of going inward and going outward. Theory of everything should include both. And I think we're not even close to that. So going in, we'll find this ultimate theory. We'll understand how space is emergent, we'll understand this and that. There'll be a huge amount of work, very interesting work, going out to longer and longer distances. In fact, what most physicists do is to take the known rules and try to derive consequences at longer distances. So when people find new materials, that's what they do. The basic laws are known. This is quantum mechanics of some atoms. And what comes out is a new phase of matter that you can use to build new devices, which are important, to say, in your cell phone. So that's what most physicists do. And there's no sign that we're close to the end there. The rules of nature, the fundamental laws of physics, are relatively simple. And the beauty of that is both that they're simple and that they lead to all these rich consequences. It didn't have to be so simple. It could have been just a mess, but that's not the case. So for this reason, I think there's a lot of work. I don't know how long it would take to find this ultimate theory, but it will not be the end of science, because there will be a lot more work to work out all the consequences of these rules. If I believe what? I can't hear you well. Can somebody else hear him? Maybe it's the microphone. A little better, yeah. It's again an excellent question, and I don't know the answer to that. So I have no idea how this thing. I have no idea how this thing will play out. And that's, I think, why it's so interesting. There's a very clear question. There are a lot of things pointing to the right end, the right direction. We have some simple examples, but we don't have a clear picture. So we don't know what will be there at shorter distances. I can answer questions about the things we do know. I think I know a little bit about that. But yeah, that thing I just don't know. It's not that I don't know, but the next speaker, he will know the answer. The answer is not no. I assume the answer is yes, but I'm not sure how. I can tell you why. So far, artificial intelligence, I'm actually very impressed by what artificial intelligence does. It's more than I expected, but it has not yet told us anything new. It kind of reproduced things that are known. Sometimes it reproduces them incorrectly. So that's a warning sign. That will probably get better with time. But I have a favorite example about that. So Copernicus found the heliocentric model of the solar system. Before that, people thought that the Earth is the center of the universe. And they measure the positions of stars and planets, and they use epicycles. How many of you heard the word epicycle? Okay, so they use epicycle. This is a wrong theory. I'll soon say why it's not wrong. It's actually not completely wrong, but they use epicycles to describe the motion of the planets. And then Copernicus said, no, we should put the sun in the center, and then we have simple trajectories, which are ellipses. This is considered a major advance. So imagine they had AI at that time. What do you think AI would have found? Would it found a better epicycle model with more accurate parameters, or will it know to completely change the picture by putting the sun in the middle? And at the moment, it looks more like the former rather than the latter. It's important to know that even at the time of Copernicus, the epicycle models were more accurate than the heliocentric model. And people say, but the heliocentric model is more beautiful because we have ellipses instead of these complicated trajectories. But the quantitative way to tell that is how many parameters you need to parameterize the motion of the planets. And at the time, the epicycle models needed fewer parameters than Copernicus needed, because they needed the parameters of every ellipse and how they're oriented relative to each other and where they are at every given time. There are a lot of parameters there, which were more parameters at the time that were needed in the thing. So even kind of the standard notion of beauty in terms of how many parameters you need to parameterize it, the geocentric model wins. Yet we all think that this is it's not wrong in that sense, but it is, the better description is in terms of the sun in the middle. What will AI answer? I asked some AI expert and they all say, oh, definitely a better geocentric model, because this was the framework where it was looking for a good fit. So maybe there's something like that. Having said that, this thing is developing. I believe it will get better. And maybe it will find, not just AI in general, computers will find better theories. And maybe there's also the logical possibility, we don't have any sign for it, but there's a logical possibility that the fundamental theory exists. We have this ultimate theory, but we humans are totally incapable of understanding it because it's so abstract and so complicated. Like if you have pets at home, and some of you already know quantum mechanics, you don't teach your cat quantum mechanics because it doesn't matter how much you try, you can guarantee that the cat will never get it. It might be the same thing is here, the theory of the universe, which some computer might even find it, will be so abstract and so complicated that we humans cannot even understand it. At the moment, there's no sign that this is the case, but I don't see why we should be the most intelligent creature in the universe, or why we should be sufficiently intelligent to understand it. So this is a warning sign. I hope this doesn't happen. We do understand it.
One of the features there's online tutors, generally was from large projects, we have to believe that one of the next steps might be really large systems, maybe some technological model that right now over years and years. And that might go into what
Yes, I sympathize with this thing. So on one hand, it goes against the spirit of this talk, if this is the case. But I would actually like to give a sign where something like this actually happened along the lines that you said. So when I was at your age, or maybe a little older, I learned that there's this cosmological constant, but it is exactly zero. People didn't know why it was zero. This was the prevailing view at the time. The cosmological constant is a parameter in Einstein's equations, and it's exactly zero, and it looks like it agrees with the experiment. And Einstein described it as his biggest blunder, introducing it. And the big question was, why is it exactly zero? Why is this the case? And sometimes toward the end of the last century, it was discovered it's actually not zero. It's a non-zero number. And it probably tells us something that our fundamental laws are not what we think they are. And there are various ideas how to get such a value for the cosmological constant. We don't have a good one. In fact, I think it's fair to say that we don't have a single one. And the experiment is undoubtedly right. The cosmological constant is non-zero. And it might tell us, it might be what it is because of something in the short distances.
Right, that's it from us. Thank you, Professor Seiberg. Thank you.
It's okay.